Okay, so we'll make a start with the presentation itself, covering the wiring regulations and changes. So what we will cover and the learning outcomes from this session are some of the main changes within the IET wiring regulations 18th edition, or BS 7671 2018 as we know them. Residual current devices and the technology behind them and their applications. Arc fault detection devices, so how they work, where to use them, and also surge protection devices, the technology with those and their main uses as well, as we progress through the slides. So the key dates around the wiring regulations themselves. So much of you, or many of you, will be aware that the 18th edition document was published in the 1st of July 2018. It is now the blue document that's in front of you on that screen. So this now replaces the 17th edition Amendment 3 that we were working to previously. The key dates to remember with regard to the 18th edition are the 1st of July 2018 when they were published, and then 1st of January 2019 is when the regulations come into effect and all installations then must comply to these new regulations. So all installations that are designed after the 31st of December 2018, this will comply, and that is an enforcement day for both new installations and alterations and additions to the existing installations. So the requirements of 18th edition with respect to RCD protection. Well, Regulation 411.3.3 has been revised now, and it applies to socket outlets rated up to 32 amps on domestic premises, regardless of what they're controlling. So no exceptions via labelling now. Exceptions from the requirement to provide RCD additional protection are still allowed for AC socket outlets that are rated up to 32 amp on non-domestic premises, but only if a documented risk assessment determines that the RCD protection is not necessary. So that's a key point there, is that it's a documented risk assessment. And the risk assessment approach, it should be the exception rather than the rule, as in most cases it can't really be argued successfully that RCD protection is not necessary. The risk assessment itself involves an appropriate electrically skilled person and a duty holder under the Management of Health and Safety at Work Regulations 1992 to cover those. And that's Appendix 10, Item 11 of the 18th edition that we're referring to. Previously, it was permissible to label the socket outlet, for example, to say for freezer use only, in order to omit the RCD protection for that socket. That's now no longer feasible, so we do need to have documented risk assessments here. In all AC lighting circuits in domestic premises, we require an RCD protection there as well. So in some cases today, RCDs are not required on lighting circuits. However, all circuits in domestic household premises must now have RCD protection. So just coming back to a few points here then, is that the risk assessment according to Regulation 411.3.3, and this is to justify the omission of RCD protection, it must be adequate. Otherwise the client and the electrical installation designer could be left open in terms of liability in the event of an incident later, at a later date. 536.4.3.2. So while 63 amp RCCBs are used in consumer units today, a study must be conducted by the installer around the diversity factor. So this is where, if there's any doubt about the protection of the RCCB, you ensure that you've got an RCCB which is equal to the upstream protective device. Okay. And then for localized protection, RCD protected wiring devices can also be considered for those localized protection scenarios. So we move on to arc fault detection devices and the 18th edition with regulation 421.1.7. It's a new regulation and it's been introduced to recommend the installation of arc fault detection devices, abbreviated to AFDDs. And this provides additional protection against fire caused by arc fault currents in AC final circuits of a fixed installation. So the regulation there gives examples where these devices can be used. So the areas that are outlined in the 18th edition now are premises with sleeping accommodation, locations with a risk of fire due to the nature of the processed or stored materials, and these are classed as BE2 locations. So these are barns, woodworking shops, stores of combustible materials, etc. Then we've got locations with combustible construction materials, classed as CA2 locations, and these could be, for example, wooden buildings and the likes. Then we've got fire propagating structures, and these are CB2 locations. And then we've also got listed locations where you've got a danger of endangering irreplaceable goods, and these are the likes of museums, art galleries, and so forth. So there's some considerations there for compliance. I suppose a topic that we list here is that it is possible that upcoming reports from recent incidents in the industry could have an impact on this advisory regulation. So a point that we show there is that it's a recommendation in the 18th, so it's an advisory regulation, but this could change dependent upon reports in the industry. If it's determined that incidents that have taken place or occurred could have been avoided if arc fault detection devices had been installed, then that could change how we actually perceive all the advisory around this regulation. A key point here is that arc fault detection devices should not be considered as the sole measure, and this is around circuit protection. So circuit design, equipment verification, installation practice, maintenance, these are all part of reducing potential risks in electrical circuits. So we still need to take into account these elements. And circuits should be designed accordingly to cater for the load requirements and be supported by manufacturers' guidance around these devices. So we now move on to the requirement for surge protection devices, also abbreviated to SPDs. So with the requirements of the 18th edition, or what was section 443, protection against transient overvoltages of atmospheric origin or due to switching, these have now been redrafted. Previously we had the AQ criteria, and this was the conditions of the external influence for lightning, and that was to determine if protection against the transient overvoltage was needed, and that's no longer part of BS 7671 now. And instead it's been reworded as a new regulation 443.4, and it requires that protection against transient overvoltages to be provided where the consequence caused by the overvoltage, and it lists A, results in serious injury to or loss of human life, and some of the areas are classed as hospitals. B, resulting interruption of public service or damage to cultural heritage. So this could be things or environments such as bus stations, museums, etc. Point C, results in interruption of commercial or industrial activity, and this could be banks, office blocks, and the likes. Then finally, affects a large number of co-located individuals. Could be a block of flats, apartments, hotels. And then another point that's in the 18th edition is around all of the cases. A risk assessment according to Regulation 443.5 has to be performed to determine if protection against transient overvoltage is required. So apologies for the technical issue we've just had there. Coming back to all of the cases. So a risk assessment according to Regulation 443.5 has to be performed, and this is to determine whether protection against transient overvoltage is required. And the exception for a single dwelling where the total value of the installation and equipment doesn't justify that protection. And I suppose a key point here, if a risk assessment isn't performed, well then protection must be installed. So we look at some of the considerations for compliance around surge protection devices and the 18th. We know lightning is still a risk, so we do see lightning strikes in the UK, but the regulations now recognise that applications that are most typically impacted by the electrical surges are those located near to sites with large switching loads. So you could be near wind farms or industrial applications or industrial environments, and industry itself. Then risk assessments to determine if the protection is needed for both residential and commercial applications. It involves a calculated risk level formula, which is denoted by CRL in the wiring regulations. And for this, the installer needs to have knowledge of the final 1 kilometre of cabling. And if the CRL calculation is less than 1,000, you still require protection at that point. But with all of that said, we can see that surge protection devices can be justified in virtually all residential applications because the combined cost of the equipment that's going to be at risk will far outweigh the cost of the additional protection provided. So moving away from circuit protection devices and looking at fire resistance supports with regulation 521.10.202, the scope of this regulation has changed. So previously it was 521.11.201, and now the new regulation, it requires wiring systems to be supported such that they will not be liable to premature collapse in the event of a fire. And this is where this regulation has now been extended. It's a significant change as the regulation now requires fire resistant supports to be used throughout the installation and not just in escape routes, which we saw previously in Amendment 3. And it ensures that wiring systems are supported against premature collapse in the event of a fire. So we've seen this come through from the previous regulations, but now you can see that it's enforced across all of the wiring system and not just in specific areas. So the considerations for compliance, so we know that there's no applications that are excluded from this regulation now. In installation of all types of premise, trunking, conduit, cabling that sticks to surfaces of the building or attached to cable support systems, they must all have fire resisting supports in place, and it's just to stop the premature collapse of these wiring systems. So a point that we make clear is, whilst not every fixing must be metal or metallic, the installer must ensure that there's adequate number of these in place to support against the collapse of the wiring system in the event of a fire. And as an expectation, we'd see that probably 25% as a supplementary measure would suit that, and that would stop any premature collapse. There is a topic point in the new regulations around energy efficiency with some advisory notes. These have actually come into the appendix or appendix 17, and the likelihood is that that will be developed further with ongoing changes in regulations. It's a new appendix that provides the recommendations for the design and erection of electrical installations, including installations that have local production and storage of energy for optimizing the overall efficient use of electricity. So you can see that there's now specific areas that are coming in around energy efficiency. And a case in note there is that it's intended that that appendix is read in conjunction with BS IEC 60364-8-1, and that's now being published. So we've covered some of the key points around the changes in the regulations themselves. We'll look a little bit more in detail around some of the devices and the devices that can be used to comply and some of the technologies that actually sit behind them. And we'll start off with the residual current devices and look at a technical overview, applications and their benefits. So a quick summary on what is a residual current device, or what we class as an RCD. So it's a device that's designed to protect and provide protection against electrocution or electrical fires by cutting the flow of electricity automatically when it senses a leakage of electrical current from a circuit. So you can see there that a device is sensing and monitoring the supply. When it sees a leakage to earth, it automatically trips the device itself. And you can see a schematic of the RCD there, and you have a device there that actually is able to sense that leakage current and disconnect the load itself. There's a number of types of residual current device, or there's a number of devices within the family of RCDs, and we can see here with a number of them and their applications. So an RCCB is a residual current circuit breaker without integral overcurrent protection. This is basically a device that would sit on a DIN rail, and it's not designed to give protection against overloads or short circuits, but it provides residual current protection. It should be used in conjunction with a fuse or a circuit breaker to provide complete circuit protection. You then look at an RCBO, or a residual current circuit breaker with overcurrent protection, and this is a combination device that provides the protection that the RCCB does, but it also provides protection against overloads and short circuits with residual current protection as well. So it can be used independently of any other overcurrent protection device within its rated short circuit capacity. And RCBOs are very commonplace in our industry now. Then we move on to SRCD. So this is a socket outlet which has an integral residual current device that can automatically switch the main circuit off at a predetermined value of residual current. So it's a different format of residual current device, and it's integral in the socket outlet itself. We then move on to FCU RCD. So that's a fuse connection unit with an integrated residual current device. So this is where you've got a fixed piece of equipment connected through the fuse connection unit, and integral to that you have an RCD or residual current device that again can automatically switch the main circuit to open predetermined value of residual current. So you can see that they're all types of RCD device within an RCD family, but they perform different functions in different applications. So we move on to some other devices which are a little bit less common. So you can have circuit breakers incorporating residual current protection. So these can be add-on devices that provide protection by adding them and integrating them to a circuit breaker themselves. An IC-CPD is more specific in terms of it's an in-cable control and protective device for Mode 2 charging of electric road vehicles. So as we're seeing more and more electric vehicles, we will start to see more and more of these type of devices as well, providing protection. And then we've got the modular residual current device at the end. And this is a device comprising of current sensing means and a processing device designed to detect and evaluate the residual current and to open and control the opening of the contact of a circuit breaking device. So a topic there with fire protection and RCDs. So electricity is a major cause of accidental fires in UK homes. And I think this has been noted by a number of reports. The London Fire Brigade have been tracking this topic as well for some time. And we have noted that over 20,000 electrical fires occur each year. And these stats demonstrate that electrical fires occur and can cause injuries, death and damage and destroy significant amounts of property. So household electricity supplies are fitted with fuses, circuit breakers, and to protect against the effects of overcurrents. The RCDs provide additional protection against the effects of earth leakage faults that can present this fire risk. And we may make a note there of an RCD handbook which is available from BEMA. There's a number of documents that we will refer to through this presentation that are freely available to you in the public domain. Many of these are from BEMA, who's an industry organisation that helps guide best practice within our industry. And as I say, these are available to you and are a good source of information to support you with your installations and practices moving forward. So as a part of the 18th edition, there is now mention around different types of RCD technologies and the different types and their applications and functions themselves. So to give you a summary, we can see here now that we're familiar with some of the common AC type of RCDs. So you can see here listed on the left. The type AC RCD, it trips on alternating sinusoidal residual current when it's suddenly applied or smoothly increasing. And this is quite a common type of RCD device that's available in the marketplace. You then move on to type A, and type A RCDs trip on alternating sinusoidal residual current and on residual pulsating direct current, whether it's suddenly applied or smoothly increasing. You can see that some of the segments that these are used in, so A, C and A are very common and they're used in residential, tertiary and industrial environments. And some of the areas that we see them in can be protecting circuits that have immersion heaters, ovens, hobs that are resistive elements, electric showers, tungsten or halogen lighting. And then when you move on to type A, they could be single phase with electronic components, single phase inverters, class 1 IT and multimedia equipment, appliances such as washing machines, etc. So for type A, the tripping is achieved with residual pulsating direct currents that are superimposed on smooth direct currents up to 6 milliamps as well. So we look at some of the more newer types that are mentioned in the 18th edition. So we've got F-type there, and the F-type RCD, it's for tripping and achieves tripping as for type A, and in addition for composite residual currents, whether they're suddenly applied or slowly rising, intended for circuits supplied between phase and neutral or phase and earth middle conductor. So for residual pulsating direct currents superimposed on smooth direct currents. And then moving on to type B, you can see that this type B device, tripping is achieved as for F-type in addition to in addition to this, for residual sinusoidal alternating currents up to 1 kilohertz as well. And some of the more specific areas that these can be used is around PV installations, electric vehicle charging points. But what you'll find is that as you work across from AC, AF, B to the right-hand side, that the devices increase in terms of the technology and the waveforms that they can actually accommodate and support. So your B type will cover F, A, and AC. Your F type will cover A and AC. Your A type covers A and AC, and AC just AC. So progressively you get a technology that can cater for a wider range. So we move on to a newer device that we see now in the 18th edition, an arc fault detection device. And we'll look at the technical overview, applications and benefits for these new technologies and new devices that we're now seeing in the marketplace. So what is an arc fault detection device? So this is a new technology and new device into the UK. We know that UK electrical fires are still unacceptably high, and we see that through some of the reports that are available in the public domain. The use of overcurrent and residual current protection has vastly reduced the risk and consequence of electrical fires, but however, due to the characteristics, electrical arcs in cables and connections can't be detected by fuses, circuit breakers, such as miniature circuit breakers, multi-case circuit breakers, or residual current devices, and such arcing can cause fires. So modern technology now makes it possible for us to detect these dangerous arcs and thus protect our installations. So arc fault detection devices, or AFDDs as they're abbreviated, they disconnect the circuit electricity supply when it detects the presence of the dangerous electrical arcs, so it then prevents the outbreak of fire. So you can see a device there on the right hand side, which is one of the iArc devices. It's an arc fault detection device which it aims to reduce the risk of an electrical fire, so it continuously analyses a large number of electrical parameters. It detects the appearance of these electrical arcs that are responsible for starting these fires, and it isolates the circuit that's concerned, which reduces the flame appearance occurrence. And there are European installation standards, the IEC 603-64. It recommends the use of AFDD devices to protect against arc faults in final circuits. Now, within the 18th edition as well, we mentioned that there is a recommendation, and the areas that we listed around the 18th, or the recommendations, were around locations with sleeping accommodations, so whether it's hotels, nursing homes, bedrooms in homes, locations with risks of fire due to high quantities of flammable materials. So these could be barns or woodworking shops or where there's stores of combustible materials. The locations with combustible construction materials. So that could even include wooden buildings. Or where you've got fire propagating structures, so such as high-rise buildings or high-rise blocks of apartments, etc. And then the final one was where you've got the risk of irreplaceable goods being damaged, so these could be museums and art galleries. So as this is a new technology, we look at what does arc fault detection devices do. So an arc fault detection device, it monitors electrical arcs that can occur in cables and connections that can cause fire. These arcs can be the result of localized cable deterioration or even loose connections themselves. So they're designed to detect low-level hazardous arcing that occurs that circuit breakers used in RCDs aren't really designed to detect. So UK fire stats we mentioned, around 2013 and 14 identified around 12% of electrical fires start with electrical distribution systems of an installation. So that's wiring, cables, plugs, and the likes. So the arc fault detection devices would detect series and parallel arcs that can occur within these cables and connections. So what is an arc? Let's start with an arc. It's a luminous discharge of electricity across an insulating medium, and it's usually accompanied by the partial volatilization of the electrodes. That's what an arc classified as. And then we can look at the different types of arc themselves. So parallel arc. So a parallel arc is where the arc current is flowing between active conductors in parallel with the load of the circuit. And what we'll do, we'll switch to some videos just to show you the instances and examples of a parallel arc.
Things like pulled-out sockets, cables squashed under furniture, and loose junction boxes are all potential dangers in a home's electrical system. Let's take a look at what happens inside an overused cable. Even minimal damage inside an electrical wire can cause dangerous hotspots. This heat will gradually burn the surrounding insulation from the inside. Eventually, enough insulation is burned that current can travel from one wire to another. This phenomenon cannot be detected by a circuit breaker or earth leakage protection system. To flow through the burned insulation, the current produces electric arcs, which in turn burn more insulation. This is how hotspots start a chain reaction that can cause a fire. Even a tiny leakage current can start a fire that can spread through the rest of the insulation and onto anything else that may be nearby. An electrical fire can start without warning on any damaged electrical cable or connection in a home. Let's take a closer look at what happens when a cable's insulation is damaged. Damaged insulation lets current flow through, creating leakage current. To find the shortest path between two conductors, the leakage current produces electric arcs. Each arc makes a tiny burn in the insulation it passes through. The burned areas conduct electricity, letting even more current pass through. This creates a vicious circle. The leakage current generates electric arcs that burn the insulation, and the burned areas conduct more leakage current, producing more arcs. When there is enough burned material, the arcs start a fire. Even a weak electrical current can start a fire in these conditions, and the fire can spread quickly to any flammable materials nearby.
So we have a look at series arcs, where a damaged conductor or connection that causes a part of the current to pass into its carbonized insulation due to a local rise in temperature.
Electrical fires can also be caused by localized electrical faults. These could be due to an overloaded cable or socket, an improperly installed socket. Any of these factors could cause connections inside the wiring to break down, triggering a fire. How? The connections gradually pull apart and overheat, burning the surrounding cable insulation and socket. This transforms the insulating material into carbon, which acts as a conductor and carries some of the current traveling through the wires, creating electric arcs. Eventually, the cable insulation and socket catch fire. The fire can then easily propagate throughout the room, spreading to a nearby curtain, the wall covering, the furniture, and so on. Do you know what condition the electrical cables and connections in your home are in? Let's look at how a simple multi-socket connector can lead to a fire. A damaged area in just one of the wires is enough to set the ball rolling. Here we see a damaged portion of a copper wire, for example. As current flows through the portion of the wire, resistance is created that generates a substantial amount of heat. This hotspot gradually burns the surrounding cable insulation. The burned area acts as a conducting material. To flow through the burned material, the electric current produces arcs. These arcs burn even more insulation, which allows for more current to flow, accentuating the hotspot and producing more arcs. When there is enough burned material, the wire catches on fire. This is how a highly localized problem with a single wire can turn into an unforeseeable tragedy.
So you can see at that point then the carbon buildup starts to conduct the electricity, the arcs increase, and then you can get a risk of fire at that poor connection or the bad termination. And that's a series arc that can be caused within a connection point itself. What we'll do is we'll move on to the actual different types of arc fault in detail. So we can see from the diagrams that the series arc fault current, it can originate from damaged, whether it's crushed, broken cables, or even loose connections themselves. And a series arc it is in series with a load and at a lower level than a parallel arc. And the series arc fault characteristics result in the RMS value of current and I²T being too low to operate a fuse or an MCB. And at this point, the protection is provided by an arc fault detection device. A parallel arc fault between a live and neutral. So it originates between your live and neutral conductors, and it's a high impedance scenario due to damaged insulation. And a fault current at this point is too low to trip other protective devices again. So your parallel arc fault characteristics, which include short duration high peak currents, result in RMS or a I²T and peak time values that are generally too low to operate the protective devices again, such as the fuses and MCBs. And at this point, you'd use an arc fault detection device again to give you that protection. Where you've got parallel arc faults, parallel arc fault currents between live and earth, that's a high impedance scenario due to damaged installation as well. But the fault current is too low to operate the circuit breaker or fuse. But at this point, the protection can be provided by RCDs and arc fault detection devices through leakage to earth. There is actually a really good guide to arc fault detection devices that's available online. It's in the public domain, and if you Google BEMA Guide to Arc Fault Detection Devices. It will give you a lot more detail in terms of the arc faults, the arc fault scenarios, and the typical types of arc fault current that can be experienced. So we look at the 18th edition again. We reflect on what the requirements are for arc fault detection devices with respect to AFDDs. It is a recommendation in the regulation now at 421.1.7 to install arc fault detection devices to provide additional protection against fire caused by arc fault currents in AC final circuits of a fixed installation. So a key point there is it is an AC final circuit, so it's not at the head of a bank of circuits or a group of circuits. It's the final circuit that we're talking about here. And you have the examples of the areas where these devices can be used. And as we mentioned, that depending on reports in the industry, these advisory or recommendations could change. But at this moment in time, with respect to the 18th edition, it's a recommendation. But it's not supposed to be the sole means of protection. So the practices around circuit design, equipment verification, installation practice and maintenance, and also ensuring that you provide full protection with short circuit, overload, earth leakage, is to form part of a complete circuit protection solution. And the circuits should be designed accordingly to cater for these load requirements and make sure that you do follow the manufacturer's guidance on these devices. So to have a look at some of the configurations of arc fault detection devices, a point I touched upon earlier was that they're not intended to be used as a sole means of protection. They must be used in conjunction with other protective devices, and that then gives you a complete safe circuit protection system. So a typical scenario here we have on the left-hand side, whereby you may have a distribution board or a consumer unit where you've got an incoming switch. Then you've got RCBO devices protecting final circuits. And then from those RCBOs, you'd have arc fault detection devices to give you that level of additional protection. And then you've also got, as a part of the 18th that we've touched on earlier, is the surge protection device. So you have there a complete system that gives you the ability for complete isolation. You get earth leakage, overload, short circuit protection, and also arc fault detection on the final circuit. And the system therein also gives you surge protection as well. And some other typical scenarios that we would probably see in the industry is where you may have a split type distribution board or consumer unit where you may have multiple RCCBs, where you might have a miniature circuit breaker protected upstream with the RCCB and the arc fault detection device further downstream. And again, we've shown you there that you've got your surge protection device giving you the protection at that point as well. So we move now on to surge protection devices, following on from that example, and we have a look at the technical overview, applications and the benefits of these devices, which we have had in the regulations previously. The focus and orientation around the regulation has changed. So we look at the danger of power surges on equipment, and what we can see is that approximately more than 90% of socket outlets have power sensitive equipment connected to them. To that you add an overvoltage and you get a resultant of potential damage. And if you look at a typical scenario in a property, with the advent of so many electronic devices and so many new technologies that we incorporate into our living spaces, quite easily in a bedroom you can have £1,500 worth of equipment. And I suppose the examples that we look at is even an iPad's in excess of £800 now. A mobile telephone's in excess of £800 if you buy that brand new. So quite quickly, as a conservative evaluation, you could be exceeding £1,500 in a bedroom space. In the living room, you possibly have a television, flat screen, home cinema, some sort of ADSL router or modem. You may have some other home entertainment devices that give you access to the internet, so forth, and give you sort of ease of access to information or play music. And you could quite easily be in excess of £2,500 there. A kitchen with microwave ovens, fridges, dishwashers, very quickly you're over £1,000 there. And if you've got a laundry or a utility area, you may have a freezer, washing machine, a dryer. You're probably going to have some sort of boiler system, an alarm. And what you can see there is that you've probably exceeded very quickly, probably £7,500 to £10,000 worth of equipment in your property. And this is, as I say, a conservative view on some of the equipment that we have in commonplace in our properties. So when we look at sort of the justification of surge protection, it sort of outweighs the additional cost of a surge protection device versus the protection of the devices and the value of the devices that you would have. So it's a point to bear in mind when we refer back to the guidance in the 18th edition in terms of the viability of the additional cost. The electrical surges. So we know that the electrical network is subject to power cuts, voltage fluctuations, for example, and we know that weather, trees, and damage to cables can cause some of these scenarios, and even power utility switching can cause these fluctuations as well. The electrical transients can be generated from internal sources, so it could be things like inductive load switching through industry nearby, etc. So these points we understand, but there's also the addition of the grid challenges that we need to take into account. And we know that there's a rapidly growing number of clean technologies that are accessing the grid. So this could be solar panels, wind turbines, EV technologies, and we didn't have these many years ago. And renewable energies that are also accessing the grid, they're intermittent. So if the wind's blowing or it's not blowing, if the sun's shining or it's not, the power produced from wind turbines, it's very much intermittent. So electricity surges into the grid can damage appliances and can even cause outages. And we understand this from the grid, and the grid does have challenges. And it's not to say that we're disregarding lightning in the UK. Although we probably think that we don't get a lot of lightning, there's still reports that show we get between 200,000 and 300,000 lightning strikes each year. And for those of you that may want to go and have a look and research some of this information, it's available on the Tornado and Storm Research Organisation website. That's Toro. And there's also a lightning map, which is on the Met Office net weather using ATD lightning detector systems. So we do see that this is tracked, and we do still have lightning strikes in the UK. And we looked at a date in time, so the 11th of July, where that month we had nearly 5,000 lightning strikes. And within that 7-day period, there was 166. And in that one day, there was 12 lightning strikes. And if anyone remembers back in May, in the south we had some significant thunderstorms and lightning. So it's not that we don't get lightning, but we do now see that the focus around surge protection in the 18th edition has moved slightly from lightning to incorporate other areas as well. So different types of lightning and its consequences. You can see there a direct lightning strike, which could be directly to the grid or a power distribution line, and it generates a surge of energy which might destroy all of the pieces of electronic equipment in your property. Indirect, you'll see that the lightning strikes a tree or something nearby, and that travels through the ground into your electrical network. And it's quite a common phenomenon where the overvoltage travels through the ground and causes damage to equipment. So we have a look at the typical electrical disturbances in power distribution networks. So we have under voltages, we have outages, we have temporary overvoltages. The area that we're trying to look at and address here is the transient overvoltages. So the surges or transient overvoltages, they're short in duration, the high magnitude voltage peaks which can damage or destroy equipment. And you can see the two different waveforms there, with lightning having 20 times the nominal voltage, and overvoltage generated by operations that could have 5 times the nominal voltage. So if you look at the waveform themselves, the lightning strikes, which are atmospheric surges, they can give you a high voltage amplitude over a very short space of time. So the unit of measurement is thousands of volts over microseconds. And it's a very highly destructive energy, whereby you're switching surges or industrial surges. You can see that it's a repetitive waveform where the switching is over a longer period of time, and that can cause premature aging of equipment, and it can even result in permanent damage of equipment as well. So we look at how do surge protection devices work. So you can see a typical scenario here with surge protection as a part of the system. What you will see is that the surge protection device is connected in parallel. The surge protection device in normal operation has a high impedance. Once the overvoltage appears, the impedance of the actual surge protection device decreases, and it allows the surge to travel through the surge protection device, bypassing all of your sensitive equipment and your system that it's connected in parallel to. So you use the surge protection device to protect all of your equipment. And the way that this is set up and arranged, you'll have a miniature circuit breaker upstream of the surge protection device, and that will trip if, for example, it's connected incorrectly. It will also provide protection when the surge protection device is at the end of life, and then also for maintenance purposes, it gives you that safety to remove the surge protection device and replace the cartridge as well. So different types of protective devices used based on lightning risk. So we have type 1, which is used where a building may have a lightning protection system. So you may have seen outside commercial buildings where there's a copper strip that runs down the side of the building. And that's your lightning rod or your lightning protection system. And that's where you would have a high risk of direct strike. And your type 1 device absorbs a very large quantity of energy at that top level. You then move down to type 2, and it's recommended to be used at the incoming point of the distribution board, and it absorbs residual overvoltages at that level. And then when you move down to the type 3 device, this is what provides fine protection to sensitive equipment. And you'll see that these are normally devices that are installed very close to that equipment, so whether it be sensitive audio equipment or sensitive data equipment, and they're quite often in the forms of trailing lead type devices. So for example, we have the APC type 3 surge protected trailing leads. At type 3, at type 2 we have multiple offers, so whether it be part of our Acti9 range, and there's multiple versions of the device, whether you have indications on the device itself, or you have Acti9 surge protection devices that actually give the ability to give remote indication. And then you also have them in residential applications through our EV9 circuit protection offers as well. So we look back at the requirements from the 18th edition on surge protection devices. We said that Section 443 has now changed, and it's now written into Section 443.4, and it's specifically around requires a protection against transient overvoltages to be provided where the consequence caused by the overvoltage can result in injury, loss of human life, interruption of public services, damage to cultural heritage, interruption of commercial or industrial activity, and affect a large number of co-located individuals. So they're the main areas that are listed in the 18th edition. A key point that I would refer to here is that the risk assessment to determine if the protection is needed for both residential and commercial applications, it involves a calculated risk assessment, calculated risk level, denoted by CRL in the wiring regulations. And for that formula, the installer needs to have knowledge of that last final 1 kilometre of cabling. And that's quite a difficult task to try and understand, because two parts of this calculation require you to understand length of underground cabling, of the high voltage and medium voltage cabling. So it's quite difficult to try and understand these pieces of information. So with that said, and the difficulties of conducting this calculation and formula, you probably see that surge protection devices can be justified in virtually all residential applications because of the combined cost of the equipment versus the risk and of the protection of the additional device. So let's have a quick look at this calculation that I referred to and the difficulties that there are in terms of finding that information. So the CRL formula is listed there, and it seems quite straightforward when you look at it at first glance. So CRL equals FENV divided by LP times NG. Okay, so you think there's three parts to this formula. Delve a little bit deeper, and you find that LP actually is derived by another formula, 2LPAL plus LPCL plus 0.4 times LPAH plus 0.2 times LPCH. Okay, so it still seems like a formula that we can work with, until we try and find out these pieces of information. LPCL, the length of the low voltage underground cable. LPCH, the length of the high voltage underground cable. And these are the areas that we believe will provide difficulties in finding this information. So then we go back to the point where if we're not going to conduct a risk assessment and the value of the actual equipment that we're protecting is significantly high, then actually the additional cost of installing that surge protection device is a means of giving protection against overvoltage and surges. So a very quick summary then of the impacts of surge protection. So we recognise now applications most typically impacted by electrical surges in the UK are those located near to sites with large switching loads such as wind farms and industrial applications. We know that lightning is still a risk, and particularly in certain regions of the country, so whether you're in the east, and you can see those lightning maps online. The risk assessment to determine if the protection is needed for both residential and commercial applications involves the CRL calculated risk level formula, which we've just identified is a fairly difficult task to perform. So at that point we say, well, surge protection devices can be justified in virtually all applications because of the combined cost of the equipment that's at risk will far outweigh the cost of the additional protection. So with that said, we've come to the final part of the presentation itself. And what we will do is open for questions at this point. And we will start to go through some of the questions that you will put forward to on the chat window. So a question we have here is that I was led to believe that the SPD should be located before the incoming switch. By installing after the MCB, won't you require more SPDs per board, increasing the size and cost of an installation? Well, we refer back to section 534.4.1.1 of the 18th edition, and it states where SPDs are required, and it states SPDs installed at the origin of the electrical installation shall be type 1 or type 2. So we said whether you've got lightning protection systems and you use type 1, or at the origin of the actual distribution board, type 2. Now, you would install it in series with a miniature circuit breaker to allow you to get the ability to perform maintenance, and also if, for example, there was incorrect cabling or short circuit, the miniature circuit breaker would provide protection at that point. But you would install it after the main incoming switch so that you can perform safe isolation of that distribution board or consumer unit, depending on the type of installation. Another question, does all the DB need SPD? So I think we've sort of covered this one where the surge protection device is installed at the origin of that distribution board, and one surge protection device protects that distribution board. So you wouldn't have a surge protection device for each outgoing circuit. It would be one for that board. So another question around RCD. Should we be using type F RCDs instead of A or AC in domestic installations due to the more advanced equipment used in most houses nowadays? So the actual topic around RCDs is to start to give guidance around the different types of RCD and the different types of application that they would be used in. So it's not to say that all RCDs will become F-type. There will be particular applications where the F-type RCD would be used. Some of the applications that are now being given more specific guidance around is the likes of EV charging units and the likes of those. A question, in most domestic properties, will it be good practice to install surge protection devices? Well, if we look at the regulation itself, the regulation is not a recommendation, it's an actual regulation to say that surge protection devices will be installed unless you're conducting a risk assessment that concludes it is not required. So absolutely, I believe that they will be a requirement to install surge protection devices. So question, do Schneider Electric provide complete product, domestic consumer unit containing all RCD, SPD and arc fault detection device? So we do have devices available on the market including RCDs, surge protection devices, arc fault detection devices are being launched as well. So there will be a number of devices available to you to support you through the transition with the 18th edition. The arc fault detection device, as I say, at this stage is a recommendation. The surge protection device is part of the regulations, unless you conduct a risk assessment that determines it's not required. But we go back to the point that you should use a complete system of circuit protection. It's not a case that you would only use an arc fault detection device or only use an RCD. You would use devices in conjunction as a complete system to provide the complete protection. So the question is, when are arc fault detection devices being launched? So they're currently being launched into the market in line with the 18th edition. And the Schneider Electric devices are due to be available at the end of this quarter and will be available for you to start to install for 18th edition compliance next year. So, questions: do all SPDs require a dedicated MCB or are some fused internally? What fuse rating do they require, and what size conductor should be used to wire the surge protection device? Okay, so there are devices that are available on the market, and some of our Schneider Electric products on the market are quick devices which give you isolation and protection of the surge protection device as well. There are some devices that are fixed, so the entire device would need to be replaced at the end of life once the indicator window shows that. Then you also have devices which are modular, so you can actually remove a cartridge and replace the cartridge, not having to disconnect the complete device. A good point around the conductors, there is some guidance in the 18th edition 1 regulations around the conductor lengths specifically, because the conductor lengths need to remain as short as possible for the surge protection device to remain effective. And there is a calculation in there for L1, L2, L3, and the length of those conductors. A question: with the image of the configuration arc fault detection devices that was shown, it looks like it could get quite messy and difficult to install in a distribution board with buzz bar due to having 2 or 3 devices per outgoing circuit. Is there a neat solution for this? So it's a new technology to the UK, and at the moment the way that the installation would be set up is that with a distribution board you would feed off a buzz bar stack with a device, whether it's an MCB or an RCBO, dependent upon the requirements, and then you would then feed that to the arc fault detection device and then going out to your outgoing circuit. So you would potentially put a extra service unit or DIN rail enclosure underneath to house the arc fault detection device. Arc fault detection devices are fairly new to the UK, although they have been used in Europe for some years. And the technology is evolving, and I expect that will start to see some changes in the coming years. As we saw with RCD technology many years ago when that was introduced, and we now have the resulting RCBO incorporating a number of different technologies. So the question: will we see 63 amp RCDs phased out in favour of all 80 or 100 amp, especially in split load consumer units? So it's not that you have to use a 100 amp RCD. You would use the RCD to suit the application and installation requirement. Now, if, for example, you can't calculate diversity, or if you require a higher rated RCCB, then obviously you can do so in order to ensure that your upstream device provides protection. I don't believe it would mean that 63 amp or 80 amp RCDs are discontinued, because they are still compliant, they still can be used. It just means that some diversity calculations need to be taken into account.